Hey class, this is Mr. Roberts at Shasta High School, and we're going to look at the homework set for section 2.2.4. That includes problems 82 all the way through 86. So if you remember in class today, we introduced this idea of dimensional analysis, looking at unit giant ones as a vehicle for turning one thing into another thing. So our first problem says a car gets 25 miles per gallon. Now that is a rate, and we're going to go ahead and let me just write that rate here. This is 25 miles per 1 gallon. And it says it travels for 45 minutes. And I actually wrote that rate over here. That's not a rate, that's just the amount of time. Right? It travels for 45 minutes. And it does that at a rate of 65 miles per hour. So you can see here I've written all of these things out, right? One of them is just minutes, and one of them is miles per gallon, and another one is miles per hour. What this question is asking is, it says how many gallons of gas does the car use in this time? Get back up here. Thank you. Gallons of gas. So we're asked to figure out this, right? Gallons of gasoline. And our input is really right here, right? We're given 45 minutes, and we need to figure out how to turn minutes into a certain number of gallons of gas required by this car. So the first thing I want to do is I can see that I've got this rate that involves miles per hour, and I want to turn these minutes into hours. So I'm going to start by writing 45 minutes, M-I-N-U-T-E-S. Now I'm going to multiply that by a giant 1, and the giant one I want to multiply it by is going to take and get rid of minutes. Oh dear, it's going to get rid of minutes, and it's going to turn that into hours. So I know that 1 hour is the same thing as 60 minutes. M-I-N-U-T-E-S. So when I'm looking at this, right, I can see that this is 45 minutes, and I can say per 1, or 45 minutes over 1. But you can see here I've got these units. I've got minutes in my denominator, and I've got minutes up here in the numerator. And if I take 45 minutes and I multiply it by this giant 1 of 1 hour is the same as 60 minutes, I'm going to change this into hours. Now, what's nice about, I mean, think about this. This is pretty powerful, right? To think about units as a tool that kind of helps us map what I need to do. And yeah, I just introduced this giant 1. I know that 1 hour is the same thing as 60 minutes. Now I could have flipped it, but in this problem I wanted the minutes to go away, and my minutes were in the numerator. So an equivalent giant 1 would, I could say that 60 minutes is the same thing as an hour. So right now, what this quantity represents, right, 45 divided by 60, those are hours. So you can see the units, the minutes are gone. I'm left with hours, 45 divided by 60, and those are hours. Now, I'm going to now introduce this rate that I have, and the rate that I have was I was traveling at 65 miles, M-I-L-E-S, per hour. Now what's convenient about that is if we look carefully, we can see, oh my gosh, I've got hours here, right? And I've got hours here. Well, my hours are now gone. So literally, if I take 45, divide that by 60, and then multiply by 65, or said another way, 45 times 1 over 60 times 65, everything that you see right now that I've written down represents miles. So it's a number, right? We'll figure out the number at the end. All I know is that product, 45 times 1/60th times 65, represents miles. Now, what we want is we want to know a certain number of gallons. And I know, Not exactly what I wanted to think, but I think this is going to work just fine. Um, I have been given this rate of 25 miles per gallon. You can see it, it's right there. It was in the problem, right? They're traveling at 20, it gets 25 miles for each of the gallons. What I need to do now is I need to convert, I need to figure out a way to get the miles to go away, and I want it to become, uh, I want I want it to become just gallons. So I have miles. I need to figure out how to do that. Well, if I'm getting a rate of 25 miles per 1 gallon of gas, that's equivalent to me saying that I get that 1 gallon of gas gets me 25 miles. Now, these are equivalent to each other, right? They're just different ways of saying the same thing, right? I can go 25 miles on 1 gallon, or said another way, 1 gallon will get me 25 miles of travel for this car. Now, what's convenient about writing it like that is if you look at the units, right? This is 1/25th, and what's the numerator? It's a gallon, and what's the denominator? Those are the miles. Now, what's convenient about that is you can see that these units, oops, get back up here, I'll use this beautiful, beautiful purple. You can see that I've got miles in the numerator. You can't see that purple. Let me grab this green. I've got miles in the numerator, and that's 2. Let's see, I'm going to literally change the color in front of you. I'm going to make this green now. That's better. So you can see I've got miles in, it's not thick enough. Mr. Roberts, quit it, just circle it. Okay. I got miles in the numerator, and that's going to cancel with these miles that live in the denominator. So if you look at it now, the only units that I have left are gallons. So if I take the number 45, let me write this in white. If I take the number 45 and I multiply that by 1/60, and I multiply that by 65, and I multiply that by 1/25, right? All of that, right? What is it? Those are just gallons, because that's the only units that are left over. So that's my answer, except it's kind of a goofy way to write it. So let's grab a calculator and go ahead and go 45, and then I'm just going to, instead of going times 1/60th, I'm going to say divide by 60, and then I'm going to multiply by 65, and then I'm going to divide by 25. And when I do that, I get an answer of, let me write this over here, I get an answer of 1.95 gallons. 1.95 gallons. So it will take me 2 gallons, right, to do exactly what it says there. So this problem is, like, I know it's kind of the first time we've seen a homework problem like this, but this is such kind of an anchor idea, and it's a totally new idea. The fact that when we look at our units, we can do arithmetic with them, and we have these things called giant ones that we can introduce to a problem. Like this right here, 1 hour is 60 minutes. That's a giant one that I just know, right? That's a fact that I know, and I can introduce that as a way of converting from minutes into hours. So wow, let's move on to the next question. But before we do move on, there's probably one thing we should say, and that's when I look at all the values that I was given, right? 25 with no decimal, 45 minutes with no decimal, 65 miles per hour with no decimal. I probably should say, just considering the accuracy of the inputs here, or the level of precision of the inputs, I should probably say that I'm getting about 2, it'll take me about 2 gallons. All right, now we can move on to the next question. Next question, it says, without graphing, identify the slope and y-intercept of the lines represented by each equation. So I've got 4 equations, and for each one I want to know the slope, and for each one I want to know the y-intercept. So I'm going to organize my work this way. For A, super nice, right? Look at this. The slope is given to me. It's 3, and I could write it as 3 over 1, or just 3, and the y-intercept is 5. The next one, B, I've got a slope of up 5 and then back 4, right? So it's negative 5 fours. And I could go down 5 and to the right 4, right? But that's the slope, 5 fours, or negative 5 fours. And the y-intercept of that one is just 0, right? I've got no y-intercept there. You could put the plus 0 if you want. The next one, C, you can see there's no x term, right? So because there's not a coefficient, there's no x term, right? My slope is just the number 0. This is not growing. It's not going up and it's not going down. And my y-intercept is 3. In fact, every value of that line is 3. Y is always 3 and x is changing. And then for the final one, I can see the coefficient of x is 4. So my slope for D is up 4 over 1, or just plain old 4, and my y-intercept is 7. Pretty straightforward. Let's move on to 84. It says the average distance of each of the first five planets from the Sun is shown in the table below. The distance to Jupiter is more or less, is the distance to Jupiter more or less than the combined distances of the first 4 planets: Mercury, Venus, Earth, and Mars. So what they're asking here is, if I was to add up this number and this number and Earth and Mars, the question is that greater than this number? Is it greater than Jupiter? Is Jupiter bigger than those? So if I was to combine these, so I'm adding these up, so I've got 5.79 times 10 to the 7th, and then I've got plus, the next one is 6.72, or 6.72 times 10 to the 7th, plus 9.3 times 10 to the 7th, and then plus the last one there is 1.416 times 10 to the 7th. So what's super cool about this is all of those terms, and let's use the correct vocabulary, right? These are not factors. I've got 1, 2, 3, 4 different terms. They're being added together. But every single one of those terms has a common factor of 10 to the 7th. So you can see they all involve multiplying by 10 to the 7th. So that's a common factor. And because that's the case, you can do this. Like if I had 3x plus 2x, you guys know that, I got some x's and some more x's, that's 5 x's. Well, because these are all 10 to the 7ths, right? I can combine those. So it's going to be a certain number of times 10 to the 7th power. But let's add all those up. So I'm going to take, and yes, I'm using my calculator, I'm going to take 5.79, and I'm going to add to that 6.72, and I'm going to add to that 9.3, and I'm going to add to that 1.416. And when I do that, I get 23.226. Now again, I'm just verifying. I'm looking here, 5.79, 6.72, 9.3, and 1.46. So I get 23.226. Now that number is not in scientific notation, so I'm going to modify it, right? To write this number in scientific notation, I know that the decimal point has to be here. I need 2.3226. Now, this number, right, this number right here is not the same as 23. So to make it the same as the one number up here, the 23.226, I'm going to multiply this by 10. So if I take that and I multiply it by 10, now this thing that I just underlined is equivalent to this thing, right? Those are the same as each other. They're both 23 point. They're both equal to 23.226. Now I've got times 10 to the 7th here, right? I'll just bring that over. So now I'm just going to combine those factors of 10, right? I've got a single factor of 10 and 7 more factors of 10. So this number is 2.3226 times 10 to the 8th power. Well, so now I can look at that. I see here the sum. This represents the sum of the first 4 planets, and I can see that the sum of the first 4 planets is clearly less than. So, and I know I'm right to say what I should say is that the average distance to Jupiter is greater than the sum of the first 4 planets, right? They're both 10 to the 8th. Oh dear, I made a mistake. Oh, I did. I made a mistake. This number right here is not a 10 to the 7th. This was a 10 to the 8th. So my little cute trick of doing that is not valid. Now I could fix it. I could say that this is, if I put this here, 14.16, that would be times 10 to the 7th. So 14.16 times 10 to the 7th is the same thing as 1.416. Ooh, you know what? I think the answer is going to flip because of that. Because now, oh dear, thank you for being here. Let's see. Now I gotta combine some different numbers, right? So I now need to add this is embarrassing. I'm so embarrassed. I can't believe this. Oh, fast forward. Let's see, 5.79 plus 6.72 plus 9.3 plus 14.16. Totally different. So this is now the number 35.97 times 10 to the 7th. So I need to make it look like 3.597 times 10, so that's the 35, and then now times 10 to the 7th. So this is now 3.5597 times 10 to the 8th power. Well, the answer is still the same, but I just would have felt awful if I would have left it like this. This is the sum of the average distances of the first 4 planets, right? Mercury, Venus, Earth, and Mars. And I can see that Jupiter is greater than that. So the question is the distance to Jupiter more or less than, okay, so I will say the average distance to Jupiter, capital J, is more than the sum of the first four planets average distance. Oh my gosh, that was a good save. That would have been embarrassing. Someone would got an extra credit point for that, but I think now it doesn't count, right? Because I caught it just sitting here talking to myself. That's why it's probably a good idea to do your homework out loud. Just sit in your room and do your homework talking. Because usually when I'm talking, I catch myself. Okay, let's move on here. So it says calculate the slope of the line passing through each pair of points below. All right, I got it. So for each one of these, right, I'm just going to say that I'm going from this first one to the second. The first one to here. I'm going to go from here to here, and then from here to here. And every single time I need to figure out my delta y and my delta x. So for this first one, I'm going to go y ends up at -1. So I'm going to take -1 and subtract where I started 2. So I can see it went down by 3. And then for x, I'm going to take the 4 minus 1. My numerator here is down 3, and my denominator is positive 3. Oh, that means that my slope, right, the slope ratio is just -1. So it's down 1 to the right 1. So the first one has a slope of -1. The next one has a slope of, again, I'm looking at the delta y over the delta x. You can see here's the y that I ended up at, here's the y that I began with. So I'm just going to take 4 minus 3 and divide that by 5 minus 7 4 minus 3 is 1. 5 minus 7 is negative 2. So my slope here, well, that's it. It's just negative 1/2. That's fine. C. So again, my y values, let's see, I end up at 5 and I began at 8. So 5 minus 8. For my x, I began at negative 8 and I ended at negative 8 and I started at negative 6. So negative 8 minus negative 6. 5 minus 8 is negative 3. And negative 8 plus 6, right? That should be negative 8, and a positive 6 would be negative 2. Negative 8 plus 6 is negative 2. And since both the numerator and denominator are negative, my slope is positive 3, not 3/3, positive 3/2. All right. And then the last one here, D. Again, we end up at 68. We started at 67. So for this one, my delta y is 68 minus 67, which is the number 1. My delta x is 50 minus 55. 50 minus 55. 50 minus 55. That's negative 5. So my slope is negative 1/5. And then there's one more little part with the great exciting stoplight here, right? And this one says Isaiah got 1 for the slope of this line that goes through these 2 points. Explain to her the mistake she made and how to calculate the slope correctly. I don't know exactly what she did, but let's look at it. Let's say that this is where we start and say we go to that point. So I'm going to take where we ended up. So I'm going to look at my delta y. We ended up at negative 1, and I'm going to subtract 2. Right, so that means my numerator here is negative 3. And then if I look at my change in x values, I end up at 4, and I began at 1. And 4 minus 1 is 3. So my slope is negative 3/3, which is negative 1. So this is this line's traveling downward from left to right. So the slope has to be this negative number. So I'm not exactly sure what she did incorrectly, but she did get the wrong slope. She got 1, and the slope is negative 1. So there's that, right? Let's move on to question 86. 86, it says, does the table below appear to represent a function? If so, write an equation using function notation. If not, explain why it cannot represent a function. Well, let's see. 0 always gives me 4. 1 always gives me 8. 2 always gives me 12. 3 gives me 16, and 4 gives me 20. So this is a function. So, and the reason why is each domain value has no more than one range value. I think I like saying it like that. I think someone in class said that, and I don't know exactly which period it was, but I like that because when you say that, it's like, okay, because some domain values can have no values. Like if I look at this right now, well, 0.5 is not in the domain, right? So never mind. But if there is a valid domain value, it can have no more than one range value. If it's got more than one, it's clearly not a function because it's not consistent and predictable. It's not always mapping to the exact same value. It's got possibly two different values. This is a function, And because it is a function, I can go ahead and write the equation for it. I can see that my x values are increasing by +1, right? This goes up by +1, and the y values are increasing by 4. 8 plus 4 is 12, 12 plus 4 is 16, 16 plus 4 is 20. So that means in function notation, right, if you give me the figure number that you want, x, and you multiply that figure number by 4, and you add 4 to it, you'll get the right value. Now, I forgot, the reason why we're adding 4 is because my 0th term, my beginning point, is at 4. So because I can see the 0th term there is 4, it is going to be +4. Another thing I really like to do is, now that I can see that, I think I have an answer, I like to take a number like 3 and plug it in there. And if I do that, 4 times 3 is 12, and 12 plus 4 is 16. So this is clearly the correct function. And it turns out, oh, that was the last question. That was 86. So yes, it's a function, and if you give it the figure number that you want, it will return the number of tiles in said figure. That's it. Talk to you later, class.